We are going to define elliptic integrals of the first kind and see how they are related to the period of a simple pendulum. So we are going to define a function f of phi, and as this integral, which we will call the incomplete elliptic integral of the first kind, the complete integral being when phi equals pi over 2. And first of all, we are just going to play around a little bit with this function. So we are going to differentiate it to obtain this expression by the fundamental theorem of calculus. And then we take reciprocals of both sides and square to find this expression. And this expression suggests that we make the following substitution, that is k times sine of phi equals sine of theta. And if we differentiate both sides in this substitution, we will eventually be able to express d phi over df squared in terms of d theta over df squared. But if we make use of the expression that we have just found for d phi over df squared, we find that this is equal to cos squared of theta by our substitution. And when we replace this value in this equation here, we will find that d theta over df squared equals k squared minus sine squared of theta. And now, since k is smaller than 1 in magnitude, we may write k equals sine of alpha, where alpha is some constant. And this means that d theta over df all squared equals sine squared of alpha minus sine squared of theta. And we can make use of the double angle formulae for cosine to rewrite this expression as a half times the cosine of 2 theta minus the cosine of 2 alpha. But now we can differentiate both sides of this equation with respect to f to eventually find that d squared of theta over df squared equals minus a half times the sine of 2 theta. Which means that if we had instead in our substitution replaced theta by theta over 2, this would give us d squared of theta over df squared equals minus sine of theta. Okay, so this we have arrived at this second order differential equation by playing around with the elliptic integral of the first kind, and we are now going to remember this before we turn to the simple pendulum. So we are considering an ideal simple pendulum, so there is no air resistance, the string is massless and not flexible, and so on. And our bob has a mass of m, and the length of our string is L, and we are going to take theta to be positive when it is to the right of the equilibrium position, but it is going to be negative when it is to the left of this equilibrium line. And we are going to resolve the weight of the bob, and the component mg cos theta equals the tension in the string, and the component of the weight, which is perpendicular to the string, has magnitude mg sine theta. And now v equals L d theta by dt, where v is the linear velocity of the bob at any point in time. And as f acts to restore the bob to the equilibrium position, this means that f and theta have opposite signs, so that f is equal to minus mg sine of theta. This means that in Newton's second law, which is f equals m times dv by dt, we have minus mg sine theta equals ml times d squared theta over dt squared, and we can cancel the mass of the bob by dividing both sides of the equation by m to eventually arrive at this second order differential equation, which resembles the one that we have previously got, so that we may suspect that t is going to be expressible in terms of theta via an elliptic integral of the first kind. However, before we try to solve this differential equation, let us make the small angle approximation in this differential equation when theta is very small, and this would give us the differential equation for simple harmonic motion. So before trying to solve this differential equation, we are going to solve this differential equation. So this is very simple to solve. The general solution is given by a cos of t times the square root of g over L plus b, where a and b are constants to be determined by boundary conditions. And we suppose that our boundary conditions is that the bob is released at an angle theta naught, which is positive, initially, that is when t equals 0, and it is released from rest. So the amplitude is theta naught. So when we make use of these boundary conditions in this equation, we find that we may take b to be 0 and theta, that is a, to be equal to theta naught, so that theta equals theta naught times the cosine of t times the square root of g over L. And now, when t equals capital T over 4, where t is the period of the oscillation, the bob reaches the equilibrium position for the first time, so that t over 4 times the square root of g over L is equal to pi over 2, or t equals 2 pi times the square root of L over g. So we see that the period is proportional to the square root of the length of the string. However, we need to bear in mind that we were not solving the original differential equation. Rather, we were solving the one where we had made a small angle approximation. However, this value of t that we got is the most important part in the true value of t, because we are going to show now that to obtain the true value of t, we need to multiply by this infinite series here, which is actually a series development of the complete elliptic integral of the first kind. And this k here, the modulus, is equal to the sine of theta naught over 2, where theta naught is the amplitude of oscillation. So let us solve this differential equation. So we already have an idea how to solve it from our initial discussions when we were playing around with the elliptic integral, but let us do it once more. So we multiply both sides of our differential equation by d theta over dt. This eventually leads us to this equation, which is the square of d theta over dt equals 2 times g over L times the cosine of theta plus c for some constant of integration c. However, we have our boundary conditions that at t equals 0, theta equals theta naught, and d theta over dt is 0. So we know that c equals minus 2g over L times the cosine of theta naught. This gives us this expression for the square of d theta over dt. And now we make use of the double angle formulae to rewrite cosine of theta and cosine of theta naught in terms of sine of theta over 2 and sine of theta naught over 2, to eventually arrive at this expression here. Now let us put sine of theta naught over 2 to be equal to k. So we are denoting it by k. And now we can rewrite our expression by factoring out k squared as follows. And this suggests the substitution sine of phi equals the reciprocal of k times the sine of theta over 2. and we may take the magnitude of phi to be less than or equal to pi over 2. So when we differentiate both sides of this substitution, we can, after squaring, find that the cosine squared of phi times the square of d phi over dt is equal to this expression here. However, the cosine squared of phi equals 1 minus sine squared of phi, and this equals 1 minus k to the power of minus 2 times the square of the sine of theta over 2 by our substitution. Which means that when we replace this in this equation and divide both sides by 1 minus k to the power of minus 2 times sine squared of theta over 2, we arrive at this much simpler equation here, which we can rewrite, in which we can rewrite the right-hand side in terms of phi by, again, making use of our substitution. Now, there is an ambiguity of sign here if we were to take square roots. However, if we restrict it to be between 0 and a quarter of the period, then theta is decreasing and hence phi is decreasing. Which means that when we take the square root in this case, we need to take the negative sign. And now this means that t is indeed expressible in terms of the elliptic integrals in this range, that is t being greater than 0 but less than t over 4. And this means that we can find t over 4 itself as the following complete elliptic integral. So we can find t itself. So this is t by multiplying both sides by 4, but we can also unfold the integrand by the binomial theorem, and then we integrate term-wise. So now we see that we have got to evaluate these expressions, which are all of this form. So this is the integral from 0 to pi over 2 of sine raised to the power of 2n of x, for n being a positive integer. And we claim that this is equal to this very memorable formula here. So the denominators are a product of consecutive odd numbers, and the denominator is a product of consecutive even numbers, and then we multiply this by pi over 2. So we are going to prove this by induction. So we denote this statement to be proved by p of n for each positive integer n, and now we prove the base case. So to prove the base case, we make use of the double angle formulae for cosine, and this eventually leads us to showing that P1 is true, and this establishes the base case, and we need to close the induction on n now, if we assume Pn to be true for some n. And to do this, we are going to consider our formula for integrating by parts. So we are going to put u equals to sine to the power of 2n minus 1 of x and dv by dx equal to sine of x, so that this integral is the integral of the sine of x raised to the power of 2n. And when we do this, we can differentiate u with respect to x and integrate sine of x to find that v equals minus cosine of x. And when we replace all this in the formula and we integrate from x equals 0 to pi over 2, we eventually arrive, after replacing the value 1 minus sine squared of x for cosine squared of x in this integral here, we find that we obtain the following reduction formula for our integral, which directly shows that Pn implies P of n plus 1, And as we have already established the base case P1, this means that Pn holds for all positive integers n. So this proves the lemma. And now when we replace these evaluations in our termwise integrated series for t, we eventually arrive at this very nice expression for the period of the ideal simple pendulum.